O, dobra, jasne.
Okay.
Czemu się zmienia ten automatyczny?
No, bo włączyłem mu ten, że tak działa ten program, ale jak mu się wróci, to on polski nie jest. Tak? Mam nadzieję. Tylko musiała, wiesz, kontrolować. Dobra, się wyciszę, bo nic. To możecie sobie zadzwonić. Ciszę. Tak. Good evening. Welcome for our weekly seminar. Today our speaker is Marzena Śniegowska. Marzena was our student. She graduated in 2018. She has the opportunity to work with Łukasz during the bachelor study and with Szymon during the master study. After that, she go for the 4 years working on her PhD in SAM with Bożena Czerny. And later she was a postdoc in Tel Aviv University working with Ben Trachenbrod. And now she got own grant, Institute of Astronomy, Czech Academy of Science. So welcome back in home, and the floor is yours.
Hello, everyone. It's actually really nice to now give the seminar in a place where I was writing so many painful exams some times ago. I'm Marzena. Now I'm working at the Astronomical Institute in Prague, so not that far from Warsaw, and you are all welcome, of course. I will tell you about the sources which are called narrow and Seyfert, and I will try to convince you why they are interesting. Yeah, I've got my own grant, which when you translate it to Polish, it's kind of like sonatina. So I can work on my own things for 3 years without having students. But so then I can focus on what I would like to do and roam around a bit with projects. So to tell you about the institute where I work on, we have 2 divisions. One is in Prague, but it's not in the city center is here. It's beautiful, of course, but our institute is also not that bad. It's on the south of Prague, and there is another division. It's, I would say, a bit like Ostrowik here versus Warsaw. In Ondřejov there are some telescopes, but also the other departments, like solar department, they all sit in this small village, so for them it's a bit more difficult to collaborate. So we have to, in advance organize seminars and everything. But it's a very pleasant place and calm. So to tell you about the motivation for the things I'm working on, in general, since bachelor, I like to work on time-dependent phenomena, different transients. And then also I got influenced by working on active galactic nuclei. And in the end, I managed somehow to merge both those things. So I guess this plot of AGN you all saw many times, but it's kind of tradition to always show it as an introduction. So in AGN, we have the black hole in the center. It's supermassive black hole, so above 10 to 5. Solar masses around, we have accretion disk, which is accreting matter, and then angular momentum has to be moved outwards. Further on, we have broadline region, where we have broad lines created. And then we have obscuring torus. And this universal model is telling us that if we are observer, for example, here, we see mostly torus. We don't see the clouds which are inside. So what we see are only the lines which are created in narrow line region. So like this one, just narrow lines. But when we are as observer, for example, it doesn't form. Here, then we see both, actually. We may have jet also in the sources. We may not. I am working on non-jetted sources to make things less complicated. And if you look at the light curves, like not much is happening there. It's just a bit stochastic variability. So this is the unification model from famous work Uri Padovani, and this is my impression of the same thing face on. Just to give you idea about the size. So this broadline region, we are like light days from the central source, and then we are like parsecs and kiloparsecs from the central source. And I will tell you mostly about narrow line Seyfert galaxies. So if we briefly come back and look at those spectra I was showing you, and you see here a beta line, which will be quite important today. And you see that sometimes it's broad, sometimes it's narrow. And I said that it depends on the viewing angle of the observer. But we have sources which are called narrow line Seyferts, which are in which this H beta line it's narrower than in broad lines, but it's not exactly narrow. It's as a narrow, I mean 500 kilometers per second. In those sources, we have less than 2000, which means that this line is still created in broad line region. So like we somehow still see broad BLR and NLR, which is this broad line region and narrow line region. If you take a look at this spectrum, also you see those two bumps around, and this is iron. And those sources are very strong iron emitters in optical, and also in UV you have it. The other thing, which is quite characteristical for them, is that the L3 lines are asymmetric. So for example, here to model the line, you need two Gaussian, one for this, thank you, for broad component, and another blue shifted, which is associated with an outflow. In different ways, then also they have strong soft excess, which is in X-rays, and they are also, they have stronger variability in comparison to other AGNs. And about the last part, I will tell you in a second. And as I said, this H beta line is important for us because we use it for many sources to estimate black hole mass. Yeah, and from this black hole mass measurements, we take a Dinton ratio, which means like we estimate how fast the source is accreting. So if we really have to understand this line as good as possible to not be biased later with our measurements for black hole masses. And for those sources, as I said, that it cannot be the viewing angle which makes us see this narrow broad line. It's probably the geometry in vicinity of a black hole. So for AGN, which are not high accrerators, you assume that accretion disk is geometrically thin and optically thick. And this is the standard model. of Shakura-Sunyaev, and we just have the black bodies, depending on the radius from the back. Whereas for those narrow line Seyfert, which are higher accrerators, probably the geometry is different, and instead of geometrically thin accretion disk, we have the inner part of the disk somehow puffed up, and yeah, like here. And probably we also have some outflows. Outflows we saw because in this oxygen line we had this blue shifted component. So in those lines we expect much more outflows in comparison to lower accreting sources. And we need to understand them because they seem somehow homogeneous, and it's good to understand homogeneous sample because then we can use them. For example, there are ideas to use them maybe in cosmology if we find in higher redshift similar sources, yeah, to do some one-to-one comparison. So first we have to understand what we have on our garden, and then we go further. And as you can see, for example, here they are kind of outliers. So we are already in our garden, we don't understand yet what's going on. So what I'm showing you here is the plane in the y-axis. We have the distance to BLR from central source. It's in light days, and on the x-axis we have luminosity of 5100 angstroms, which is assumed to be just continuum. There are no lines there, and most of AGNs are following this relation. And the color coded, we have accretion rate. So the darker, the faster, the more they accrete, the matter. And you can see that our narrow line Seyferts are here. So they are not following the same relation. And then the question is why? Why they have the, if we measure their H beta lags using reverberation mapping. So in reverberation mapping, you take a point from continuum, and then from time lag, also the light which is reprocessed in broadline region is coming towards you, and it's speed of light. So the velocity we know, the time we will measure from light curve, and then we have this R. And for those sources, it seems that this H beta line is probably closer, which is very peculiar. And we wanted to verify that using independent method, because we wanted to understand if really we have lower black hole masses and this H beta is really made closer to black hole in comparison to those AGNs which are nicely following the relation. And we choose our candidates quite nearby sources, and you can see that they are very pretty, especially this Markarian one, with which I have kind of love-hate relationship. You will understand in a moment why. And you see that in black hole masses, they are rather on the lower side for me, because for me, I mostly work with 10 to 7, 10 to 8 black hole masses. So those were relatively low, and this mass is measured from reverberation map. And now I will tell you briefly about the instruments. So we decided to use spectropolarimetry technique, which I will explain you briefly in a couple of slides. And we used spectropolarimeter, which is on VLT. And the program was written by Bożena Czerny. She applied, it was her idea to do so. And we measured only 3 objects because this technique is extremely costly in a sense, also with money, but also with the time of the telescope. And also we measured H alpha line instead of H beta, which I showed you, because around H beta you also have iron. It can be, we weren't sure how it will behave. In H alpha you don't have those lines around, plus it's higher intensity. So because with spectropolarimetry you will lose a lot of flux by doing polarization. And for each also we needed to measure polarized star and polarized star just to understand if we know what we are doing. And for each source, you will have like the spectrum, which is divided in the prism in an ordinary beam and extraordinary beam. And then also for each of this beam, we have different angle on which we measure. So for one source, in let's say one exposure, we have 8 spectra with which we have to work on. So you see it's already 8 times more than using normal spectroscopy. To reduce the data, we use ISO reflex, which is a program provided by ISO, but because of this Markarian, I wasn't sure that I understand what I'm doing, so I also did it with IRAF, very like, step by step, as I was taught here at the observatory. And I've got the same results, which I will show you later. And this program is a bit more intuitive in comparison to IRAF. I don't know if you had pleasure to work with IRAF on the terminal. Here you can click a lot of things, and I'm a rather clickable person, so it was a bit more pleasant to look at the data and nice photos. And here you can see this extraordinary beam and ordinary beam of Markarian. So to briefly tell you about spectropolarimetry, we there measure, I would say that you can measure things with photometry, with spectroscopy, and with polarimetry. And in polarimetry, you will measure the part of the source where you have scattering. And the scattering can be done on free electrons or dust, or maybe some magnetic fields, but then it will look differently on observations. And you have to calculate something which is called Stokes parameters. And I think like in physics, we had those things in our studies. I will talk only about linear polarization. So this Q and Q, which you see up, this is for circular polarization, which I just wanted to show you, but we will not talk about this part anymore. So as I said, for each source, we had 4 different angles with ordinary, extraordinary beam. Then you calculate the flux. Then you have to calculate those 2 parameters, and then you get how much polarization is on your source. And as you can see, like it's quite easy math because we are adding things, removing, multiplying, but very important is to, and I've learned it, that you cannot mess up because later you will not understand what's going on. So you have to be quite careful on this part. And here I wanted to show you the result, this P, which is polarization fraction, one for polarized star and one for unpolarized. And you can see that for unpolarized, we have about 0% polarization, whereas for polarized star, we have like more than 5, around 10, it's assumed to be polarized source. So now, okay, I understood the method. I reproduced things as they are in catalog. So I think I can move on to our sources. And now I will tell you about this Markarian 1044. So here you see the non-polarized H alpha, and here polarized. And for both of those spectra, we can measure full width. And because of the geometry I told you earlier, we assume that H over R, which is the height of the disk versus the radius, so it's like a funnel-like shape, is 1/3. And then we can estimate the viewing angle on the source. And then also later we wanted to measure black hole masses, but just as an extra thing, we wanted also to see how it will look, the viewing angle for those sources. And here I wanted to show you all sources for which we did that. So there is our Markarian, SDSS, and you can see that we have here 2 components. One is narrow one, and then the other broad one. And the broad one you use for estimating black hole mass. And here are sources which are polarized. So you see that they look different than unpolarized one, yeah? And that was the main purpose. I wanted to show you all of those nice plots. And all those 3 sources, they had low linear polarization, below 1%. So now we will come back to the viewing angle. And we estimated it using the formula from the literature. And here are our results. And here it's kind of the problem that we have nothing to compare it with. Yeah, only for Markarian, we found that there was one work in which the group measured the viewing angle using XMM Newton, but then in XMM Newton you measure it closer to black hole. So if, for example, disk is misaligned, then it would not be, yeah. But since we are quite close, so probably it's not misaligned, the accretion disk. And for the other, actually, we could do the same if we apply for XMM. So if someone would like, there is project idea. And here we estimated black hole masses using this full width, which is polarized. This distance to BLR we used from the literature, actually. This we know, this we always assume 1F, because in this parameter, we assume a lot of things about how clouds in BLR are located, how they are shaped. So it's difficult. We don't know that. But you can see that the order of magnitude, like they are still small. It's not. We didn't go to 10 to 8. So in those sources, we really have the small black hole masses. And then, since we already had the data, we decided to also model the geometry of the sources using code Stokes. And Stokes is radiative transfer code, in which you assume like number of photons, which are spreading isotropically through different media. And then you assume what would be the medium on which you work on, and you assume which kind of scattering it would be, if it would be scattering on dust or on electrons, or you can add magnetic field if you wish. We worked on mostly electron scattering because we are in BLR, and dust you rather have in torus, which then it would be in infrared, and our observations were in the optical. I mean, just for a checking, we tried also to, if we can reproduce our results, which I will show you with the dust, and we could not, like it was too low intensity. So it was electron scattering. And then, you play like with Legos, trying to match observation. So here are assumptions. We tried 2 different models in which we have this continuum with our photons, which are then reprocessed in BLR, for which you assume the shape and also where it is located. And then we have scattering structure, which is not exactly torus, it's before the dust torus. And because of Markarian 1044, we also had to assume extra component. And here it's our favorite source, I told you. So here we have observations in polarized light. And here we have beam observations, which are here on the gray, and the model, which is in red. And you can see that if we use only this, the intensity, it's not enough to reproduce the peak. Yeah, in residual, you see there is this huge bump. So that's why we decided to add this polar scatterer, but we didn't know where exactly to put it. So we put it like 90 degrees above in the same location as the scatterer here. And then you can see that the shape is matching much more in comparison to just this geometry. And it took a lot of time to figure it out. And because of this peak, I was redoing the whole data reduction in IRAF, because we thought that this is maybe, we weren't sure this is physical effect. We thought that maybe we messed up something with data reduction. But if after using 3 different methods, we were getting the same, then we decided to dig in more in the code to reproduce it, and we got it finally. So it's very nice. And then also we wanted to play a bit more with the opacities. And here it's chi square versus the ratio between opacity of the polar source versus equatorial one, which is this one. And what we found is that in chi square, like with the data quality we had, we cannot tell if the scattering structure above is optically thick or optically thin. Like there is not that much difference in chi square, so we would need better data quality to proceed with that. So this is the first part of my talk. So we wanted to achieve the viewing angles, which I showed you. We kind of managed. We wanted to determine black hole masses and to model the scattering regions. So this we did. And then that we need really this polar scattering for Markarian. The other sources were more well behaved, I will say. And now we will go to flares, which we may have in narrow line Seyfert. So now the sources about which I told you, the geometry, this will be our background. Yeah, and we will be more interested what is going on the top of that. And in the literature, we have, I would say, quite nice sample already of those narrow line Seyfert related flares. And I showed you earlier that in general, for AGN, we rather have some stochastic changes. But here you see that we have some flares with quite complicated shape, different from each other. This with some like double hump. If you look at spectra, it's even more complicated. Like we may have some additional lines which are showing up in some sources. In some sources, no. For this source, for example, which is exactly the same one, after the flare, from here, we got a lot of iron, which exactly look like narrow line Seyfert. So then also the question is, maybe some sources which we observe as narrow line Seyferts are kind of transient light. So I think we have around 10 sources like that. And now with LSST and those all surveys, which they will look for things like that, we'll have even more, and which is quite nice. I think we will have the whole zoo of different things, and a lot of models will be needed to understand them. And now I will tell you briefly about TDEs, which are in the galaxies, which are quiet. Yeah, assume that there is no accretion disk inside. And those events are very luminous in optical and in UV, as you can see here, the light curve, with a very broad helium and sometimes hydrogen lines. And here you have the example of helium. This is very broad. I was showing you the sources with 2,000 kilometers per second. Here we are talking about 10,000 kilometers per second. And they are in galaxy centers always. They are more luminous than supernova. Spectra look different also. And this is important that we don't have accretion disk before the TDE. When we have TDE, then the matter from the star is creating temporary accretion disk. But in narrow line Seyfert, we have already the disk, yeah, with this funny geometry. But we also have stars there. I didn't mention anything about stars, and most of AGN people don't, because what we will say about them, we see them maybe as a population, we can model them, which is not done that often. And when we have stars there in accretion disk, probably they will evolve differently because we have medium which is around them. So this evolution will look different than we assume normally. They may come close to black hole, and maybe they will be disrupted. And then maybe the light curve of TDE will look different because we have different medium around. Yeah, so it may react with it, depending also on the density of accretion disk. So it's quite complicated to do. Yeah, so as I said, we have transient zoo in narrow line Seyferts, and in AGN, in classical AGN, where we don't have much changes, we just see stochastic variability. in TDs, we see those nice light curves. In most of the cases with power law, 5/3. And as I told you earlier, for those sources in which we know that host is narrowly Seyfert, it's very complex what is happening, and it's not that much comparable to the light curve of Ghazari et al. I was showing you here. Yeah, like here we have some second bump happening here, something else. So it's very interesting to do, and it seems that even within the group they vary between each other. It's hard to find the same sources within those. And I will tell you mostly about this source PS 16 DPM, and 16 means that it was observed in 2016. And here we have the light curve with some kind of like a double hump. And then with those nice spectra in which you can see a lot of iron, and it looks exactly like narrow Seyfert. I also had pleasure to work on source similar to this one with these extra lines, this 80, 2017 BGP, which was also in AGM. So we will focus on this flare and exploring it. And there is very nice work done by Tania Petruszewska, and you see that this work was done 7 years after the flare was noticed, with the very dense monitoring in UV from Swift, in SDSS, and also in other telescopes. So we have very dense monitoring, and you also see that depending on the filter, the light curve look different, but this M here kind of stays, which is quite funny to me. And the spectra you already showed, that they are very nice. And also it's a beautiful collection of spectra, no? It's very nice. And I think in transient in general, the more data you have, the better, but sometimes also the more confusing. Yeah, and I will stress it again, that it looks exactly like narrow Seyfert. If I didn't know that there was a flare, I would just say, it's typical narrow Seyfert, nothing that much interesting there happening. And in this source, we know that it is an AGN. Actually, it was narrow Seyfert, but not really typical one because we don't have iron around. But we have broad line region here because we have the broad component in the emission line, from which we can estimate the black hole mass. But we know that we have BLR, which means also we have accretion disk, from which BLR is getting ionized and producing lines. And then on top of that, we have this beautiful flare, like this one. So we decided with Marzena Śniegowska to do very simple exercise because we are simple AGN people. We don't know much about stars. So we decided to assume this flare from point of view of accretion disk. So we call it actually like a mass deposit. And we were putting mass deposit, which was spreading viscously. And we were checking how many of those we need. It was just like delta Dirac computing, so it was as simple as possible. And how many of them we need, and how much mass we should put there to reproduce the shape of the light curve, especially this kind of M I was telling you about. No? So for a single deposit, of course, we cannot reproduce this thing there at the beginning. And of course, the more events you add, the more you play around, of course, the better T-square would be. But we decided to stop at 5. And what is amazing here is that in all of those, we were putting almost exactly the same mass, which is 0.3. And if you think about initial mass function, what are the stars which are the most common around? It's 0.3. But then also the question which we still have, and we don't know the answer, if it was really a star, or maybe it was just the shell, the atmosphere of the star, which is bigger. Because we had accretion disk, so maybe they evolved differently. So maybe in accretion disk, the population of stars look different, kind of. But it's hard to say without proper modeling of spectra. Maybe from spectra we could get that information, but we didn't do that. But for sure it was stellar mass thing which was disrupted there. And when we were observing it, here you can see the SED, which is spectral energy distribution. You see that we can actually more or less model it with blackbody, but we have to add also the part from broad light region to match it nicely. And those temperatures are very low if we talk about something which was happening quite close to black hole. So we were wondering why it's so, why in Swift we observed such a small temperatures. And then we thought that maybe what we see, it's like, here it's like a zoom-in version of black hole and accretion disk. And before the event, we had the black hole, then accretion disk, and the BLR, which we know we had because of the spectra I showed you. And it was like, you know, pretty normal situation. Then we had some kind of, which we call event, which happened in the vicinity of the black hole, which ionized the upper part of BLR. And this is what we see. So we don't see exactly the event inside, but the reprocessed light. That's why the temperature is lower, probably. Yeah. And this is my take-home message. Another, that for this source, probably we have the mass, which was injected during this event, is something around 0.3 stellar masses. We needed to reproduce this M at the beginning. We needed 2 events separated by 4 days. And we know that it was an active AGN. So then the question is, how common are some TDs which are hidden in AGN disk, and how to tackle them from observations, which maybe it will be less complicated than starting to modeling them when you have to take a lot of things into account. But it will be also very exciting to do. Yeah, that's it. Thank you.
Thank you.
Thank you.
Time for question. Lukasz, I see that you have one.
We have considered binary system. If we see only 4 days difference and the event lasts so long, then it could have been just binary. First picture could have been 0.3, but you have stars in binaries.
That is true. And they are quite common. Yeah. I didn't, yes, actually, yes. So then what? It would be just like a atmosphere of them peeled out a bit. Maybe. That would be fun exercise to model and to check. Yeah.
And have you tried other masses?
Yes, we tried, and then the luminosity was too high. So we
So you
tried.
can have, you know, binary, you know, 0.15 plus 0.15, that will remain.
For example, yeah. Yeah. Okay. So then another thing to do.
Marcin?
And this, there is estimation of mass of this AGN.
This one I showed you. This one, yes. It was 10 to 6 around, so it's like a narrow line Seyfert. They are all kind of 10 to 6 solar masses.
Like our Milky Way twin.
Yes.
Yes.
So this, at the very beginning, you show this unification or
Yes.
unified view of AGNs, right? That the difference between them is mostly from the angle of how we see them.
Yes.
Is this like widely approved by the whole community right now, or is there a discussion about this?
No, there is always discussion, because also here recently discussion it was about the torus, that it's clumpy, that we have some clumps. About the BLR, I think there is still ongoing discussion. what is exactly the geometry, if it's spherical or it's kind of like sandwich-like with accretion disk.
Okay, but there is a common agreement that it's all because the difference between characteristics of different objects is because of the viewing thing.
Yes, but if you start to talk about changing look AGN, where about them I did not mention here, but there are sources for which you cannot change the viewing angle, yeah, because like we are staying in the same place. Also, the source will not wobble in 10 years. And in those sources, you see the change from narrow to broad. And then the question is, what is happening there? So
And it's an open question.
it's rather open question. I think for now the agreement is that it's some change in photoionization, that it's some accretion thing, not obscuration. But what exactly is happening with accretion is still open.
Agnieszka?
Oh, I want to make sure because as far as I remember, these narrow line Seyfert ones used to be defined according to the relatively small masses of the black holes and very high eddy ratio.
Yes.
Seyfert lines.
Yes, but
Which you study and how this could affect the TDE events if it makes such like eddy relations.
this I don't know. But about the definition, also another thing which is defined for narrow line Seyfert is the ratio between H beta 203, which should be less than 3.
Yeah, this
Yes,
is
yes, but
definition from the observation.
From
I read
observation.
about interpretation, which may be disputable, but that was the interpretation some time ago, yeah.
yeah, so
They are trying.
and I think it's like in agreement with observation that because also for this higher accretion, the shape of lines is a bit, okay, maybe you will not see, but it's more like wing. You have more wings on the bottom. Also. And another question, there was one.
But about modeling, what would you take to account, want to model final disruption of the star, it's like this very highly.
I don't know, to be honest. I think we could start to. I think there was one work in which they were checking how the stars are evolving in the denser medium, which would be accretion disk. Now there will be soon one work on archive where one group was putting star through accretion disk to see how it will go, but the star is not disrupting, it's just going through the accretion disk. I think the most fun thing to do would be to see this tidal disruption happening somehow in this dense medium, but then I don't know if we would be close enough with accretion disk to do so. I don't know, but I think mostly I would start to play about the medium around the star as a first choice. And then also you could try to model the spectroscopy using photoionization code to see if whatever you assumed will match the observation. So maybe that would be also another thing to do, which I don't know how to do. So if someone knows, go ahead.
Łukasz, next question. No? Okay. So we have now online question as well. So let's thank our speaker again. And see you next week. Thanks.
Dziękuję, że ogarnąłeś.
No, nie ma problemu. Na sprawę.
Jest